include brain deformation estimators for head impact to unsupervised domain adaptation and deep learning. So Xianghao, 10 minutes hand wave, 12 minutes hand wave. Thank you.
Okay, good morning everyone. I'm Xianghao Zhan from Department of Bioengineering at Stanford University. Today is my great pleasure to present my work, brain strain estimation with the unsupervised domain adaptation. So before I get started, may I ask, how many of you are horse riders or bike riders? Yeah, thank you. Don't forget to wear the helmet. And my second question is, how many of you are fans of contact sports? Yeah, me too. As a hardcore sports fan like me, the word traumatic brain injury has never become an abstract one, because the traumatic brain injury, or TBI, has become a global health challenge. It affects more than 55 million people worldwide and contributes to more than 2 million emergency departments visits in the US alone. And it can be caused by head impacts originated from car crashes, various contact sports, accidental falls, and even domestic abuse. What also needs our attention is that more than 80% of these TBIs are mild, which means that they are harder to detect, but the brain damage could accumulate. Because after our head gets impacted, there is brain strain that tissue stretches, and this could lead to axonal injury, blood-brain barrier disruption, which could progress to the neural inflammation, death of neurons, and brain edema. And repetitive traumatic brain injury could lead to long-term consequences such as neurodegeneration and even chronic traumatic encephalopathy. Therefore, as a researcher in this field, I'm always thinking of better ways to detect the dangerous head impact and seek for prevention of the damage accumulation. Well, strain and strain rate in the brain has been shown as effective injury predictors, and the state-of-the-art method to compute these metrics is called the finite element modeling, or FEM. It uses the head kinematics that describe head translation and rotation that could be measured by sensors like the instrument in Moscow. And then this is what's happening in the brain and how to compute it with the finite element modeling. However, the FEM is too computationally costly, and this limits its application in the clinical applications. To accelerate, researchers, including us, have developed the machine learning head models with the same input and output as the FEM, but the only difference is that it uses a deep neural network as its kernel. It is pretty quick, but it has its problems. For example, in our previous studies, we have found that the accuracy decreases sharply when the training and testing datasets are from different types of head impact. We may get high accuracy on the simulated impacts, but the accuracy decreases sharply once we predict on mixed martial arts impact, for example. And although we could train large models on large quantities of simulated impact, it's almost impossible to train models on a small real-world impact dataset, or what we call the impact domains. And these observations lead us to believe that the machine learning head model trained on a particular dataset may overfit to the dataset-specific characteristics. However, the ground truth biomechanics relationship between the kinematics and brain deformation should be invariant of the dataset-specific characteristics. And therefore, we could probably leverage the domain adaptation to mitigate these domain-specific or data-specific characteristics. To test whether the domain adaptation works, here we collected 5 datasets. Firstly, we collected simulation datasets with over 12,000 impact datasets. And here we also collected 2 target datasets as the validation datasets. Here the football 1 dataset, which are the impacts collected before the pandemic, and also the mixed martial arts impacts. We also collected 2 holdout test sets from the target dataset, the football 2 dataset, which involves the dataset that collected after the pandemic, as well as the boxing data. And here, I'd like to mention that the validation datasets are used for model optimization and the selection of the best performing unsupervised domain adaptation models. Once the models are fixed, we will evaluate the model's performance on these finalized holdout test set, which has been kept out of the training process. And the input to our models involves 510 kinematic features that have already been proved effective in predicting strain and strain rates in our previous studies. And it involves four kinematics: the linear acceleration, angular velocity, angular acceleration, and angular jerk. Of course, 4 channels for each kinematics. We have also extracted both temporal features and spectral features from the waveforms, and the details and rationales could be found in our previous publications. To test whether the unsupervised domain adaptation works, firstly, we developed a basis model that is going to be used as a baseline to be compared against. Here, we train a model on the entire over 12,000 simulated impacts with a 5-layer neural network that has been used in our previous study, the same structure, and we will use this basis model to directly predict the target impact. And the first unsupervised domain adaptation approach we propose here is called the domain regularized component analysis, or DRCA. The key idea is try to find a domain invariant feature subspace that minimizes the between-domain data spread. And here, I will use the visualization in 2D feature space to briefly introduce this method. For example, the source data and the target data have to spread out because of their specific characteristics, and they may spread out into 2 clusters. And what DRCA wants to do is trying to find a projection onto a line, which is a 1D subspace, that after the projection, these 2 dataset projections overlap, such that their between-domain data spread are minimized. And with this projection, we can train a machine learning head model on this projected data with the drift compensated. And the second approach we use here is a deep learning approach, which is a cycle-generated adversarial network, or CycleGAN. And the key idea is to find a target domain to source domain translator by training 2 sets of generators and 2 sets of discriminators. For the discriminator, the training goal is try to classify whether the data comes from the same domain or it is generated from another domain. While for the generators, the main goal is to generate more realistic data to fake the discriminators. And once we train the model, we get the translators and translate the target domain data to the source domain data and leverage the basis model. And here are the methods. And how well does this model perform? And well, here comes the result. Firstly, on these 2 validation datasets, the football 1 dataset and the mixed martial art dataset, here we predict the maximum principal strain and the maximum principal strain rate. Here we evaluated the mean absolute error and the root mean squared error in the estimation. And as you can see from the results, the DRCA approach, which are marked with the boxes, shown significant reduction in brain strain and strain rate estimation, and reduction in mean absolute error, or MAE, could range over 30% to over 19%. And to visualize this reduction, here we plotted 2 example cases. The first column shows the reference result given by the KTH finite element model, which we used to train the model. And the second column shows the predictions given by the DRCA approach. And the third column shows the baseline prediction. We can see that visually, the DRCA reduces the error in brain strain and strain rate estimation, and the high strain region and high strain rate region predicted by the DRCA model is much closer to the reference model when compared with the baseline. Well, till now, all the results are on validation datasets, where we could optimize model tune hyperparameters to show good results. So how really does the model perform on these holdout datasets, which are completely unseen? Well, here comes the result. On the 2 holdout test sets, firstly, in the estimation of brain strain, we can see that the model, the DRC model, reduces the mean absolute error in the estimation of brain strain at over 19%, 18% to over 38%. And similar results were found in the estimation of strain rate, and the reduction ranged from 19% to over 29%. And the accuracy and the error was much smaller than the concussion threshold that has been found by previous researchers. And to sum up, what has been done in this study is we try to use the unsupervised domain adaptation to improve the machine learning head model's accuracy in estimating the brain strain and strain rate, particularly across different types of head impact. And here, by saying unsupervised, we mean that we do not need to use any FEM labels that are from the target dataset. So we are going to provide our users with a 2-stage model that combines the DRCA with the machine learning head model. And the users simply need to input their on-field dataset, and this model will take care of the data and output brain strain and strain rate. As for the application of study, And this model could help the athletes and medical professionals in different sport teams to monitor the whole brain strain and strain rate and seek for the medical inspection and early intervention in time. And for researchers at the machine learning head model, this two-stage model could also help them shorten the time for the head impact analysis to be over an hour, with the FEM to be within 1 millisecond for the machine learning head model. And that's all of my presentation. If you'd like to try out our first version of machine learning head model that has already been published, here is a QR code to the compiled version. And yeah, if you do not know Python, it's fine because this compiled version is very user-friendly. And yeah, you're more than welcome to try that. That's all of my presentation. Thank you very much for the privilege of your time.